In this problem, we're asked how much energy is needed to change 50 grams of ice at negative 30 degrees Celsius to steam at 140 degrees Celsius. The key here is that it asks how much. So whether it's how much energy is needed, how much heat is needed, how much energy is added, how much heat is removed. The how much part is the key. It'll be this type of problem. What we have is I like to always just make a road map here of what's going on. And we start with ice, and it's at negative 30 degrees Celsius. And we're going to end at steam, which is at 140 degrees Celsius. Now, a common mistake is to just use MC delta T and use our change in temperature as 170 degrees Celsius, but that would not be correct. Again, we're going from a state of ice to a state of steam, so solid to a gas. We're not dealing with sublimation here, we can assume. It would be analogous to just being teleported from Pennsylvania, let's say, to Virginia. It can't happen. Instead, we have to go through the state of Maryland, or in this case, the state of water, before we can get to the state of steam. So when do these borders occur? When do we change from ice to water? Well, we change that at 0 degrees Celsius. So it's like the Mason-Dixon line, going from Pennsylvania to Maryland. And so when do we change state of water to steam? When do we go from Maryland, let's say, to Virginia? Well, that occurs at the border, which is, in this case, 100 degrees Celsius. So what we're actually going to do is figure out how much energy is needed to increase the temperature to 0 for ice, and then figure out how much energy is needed to melt the ice, and then figure out how much energy is needed to go to 100 degrees Celsius in the water phase, and then figure out how much heat is necessary to boil the water, and then figure out how much heat is necessary to finally go to 140 degrees Celsius in the steam phase. So we're adding up all these little sections. So we're going to find a total Q. Now the first thing we do is we go through a temperature changes ice. The hottest ice can get is 0 degrees Celsius under atmospheric pressure. So you can't get any hotter than that. So we're going to go MC delta T for the ice. The temperature change, Q is MC delta T. But now, again, to keep my analogy of actually going from state to state, we have to stop and pay a toll. Before we can get any hotter, we actually have to melt the ice. So that formula is ML. The heat necessary to change phase is ML. In this case, it is melting, so it's MLF, latent heat diffusion. So now that we've actually changed over, we are going to increase, or we're going to continue on our journey through the state of water, or Maryland, or whatever you want to say, and we're going to now go through a temperature change, MC delta T, while we're in the water. Now the hottest water can get is 100. You can't get any hotter than that. You have to change phase before you continue into steam. So again, we're going to have to stop at the border and change phase, which is ML. In this case, we're boiling, so it's a latent heat of vaporization, before we can proceed any further. So now we're going to go through our final temperature change. Now we're steam at 100. Both steam and water can coexist at 100, and both ice and water can coexist at 0. These are the only two temperatures where we can have multiple phases for H2O. So at this point, though, we're going to increase our temperature to 140. So that is an MC delta T. It's a temperature change. And so now we're going to put in all of our values and solve. Before we put in our values, let me just mention, though, that the melting and the freezing point are the same temperature. If I'm going from Pennsylvania to Maryland, I cross the border at the Mason-Dixon line. If I go from Maryland back to Pennsylvania, I cross at the Mason-Dixon line. So it just depends on which direction we're traveling, but the border, the temperature at which we change, is the same for both. So now we can put in our values. So the mass, we've got to be careful, this is in grams. All of our specific heat capacities and latent heats are kilograms. So we've got to change it to 0.05 kilograms times the specific heat capacity. Now here's where this little map helps out. We are in ice. So the specific heat capacity of ice is 2,090 joules per kilogram times degrees Celsius. Next, what we're going to do is multiply by the temperature change. We increase, so that's a positive, we increase by 30 degrees Celsius. Next, we're going to figure out M times LF. Again, the mass is 0.05 kilograms. Latent heat of fusion for H2O is 333,000 joules per kilogram. So we've taken care of that as well. I'll kind of underline them as we take care of them, just to keep track. Next, we have MC delta T while we're in the water phase. So again, I'll look above to see what it is that we're actually doing. And so, I'll write it down here. Plus, we have the mass, 0.05 kilograms, times specific heat capacity of water, which is 4,186 joules per kilogram, times degrees Celsius, times the temperature change while we're going from 0 to 100 while in the water phase. At this point, we are going to again change our phase, M times LV in this case. Mass is 0.05 kilograms. Latent heat of vaporization is 2,260,000 joules per kilogram. Again, we just looked that up. And then finally, we're going to increase our temperature by another 40 degrees, from 100 to 140. And we'll do this while we are in the phase of steam. So look up specific heat capacity of steam to be 2,010 joules per kilogram times degrees Celsius. We have gone up in temperature by 40 degrees. And so we get an answer, and our answer comes out to be that the total heat added is 157,735 joules. Now before I leave here, just watch out for the values. Again, latent heats could be negative, and watch out if your temperature changes are positive increase or negative decrease.